Hello everybody, welcome to Unit 2. This is Conductors, Capacitors, and Dielectrics. Let's get started. So we're first going to talk about conductors. And just recall that a conductor contains charges that are not bound to an atom and are free to roam around. And remember, conductors and the opposite of conductors are insulators, where charges are literally stuck to the atom and they're free to kind of, be polarized, but they're not free to roam around like a conductor. Now, electrostatic equilibrium is when there's no net motion of charge within the conductor. So you can kind of think of this as all the charges are kind of settled down, and there's no net motion of charge. The charges aren't moving around. Now, a few properties of this. So the electric field is zero everywhere inside the conductor, whether the conductor is solid or if it's hollow. And this is just because everything gets evenly spaced. If the conductor is isolated and carries a charge, then the charge resides on its surface. So this is saying that if you have a metallic sphere, for example, and there's a charge on the sphere, then the charge, which are like the particles, like the particles are going to be residing around the surface. So that's where at electrostatic equilibrium, after everything's settled down, they'll all be on the surface. The electric field at a point just outside a charged particle is perpendicular to the surface of the conductor. So what this is saying is that if you have, our metallic sphere example, and remember, the charges are going to reside on the surface. So let's say we have a positively charged sphere, then the electric field is going to be perpendicular. So it's always going to be perpendicular to the surface here. Now, on an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest. So what this is saying is that, let's just break this down. So the radius of curvature is the smallest. So if you have some kind of curve that looks like this here, blah blah blah, and it has like another arc over there. In this portion of the surface, you can see the radius of curvature is pretty big, but over here, for this little curved surface, the radius of curvature is very small. So if this is our irregularly shaped conductor, then the surface charge density will be greatest in this area over here. And yeah, this just might come up as like a multiple choice question, or it might be like a part A on an open-ended. Where is the surface charge density the greatest? And that's where you just look to see where is the radius of curvature the smallest. All right, conductive surfaces. So an equipotential surface, and this is just a surface where all the points have the same electric potential, has a property of having no electric field within the conductor. So if you think of a metallic sphere, and by symmetry, all the points on the sphere, so if I have a sphere over here, by symmetry, all of these are going to be, they're going to have the same electric potential. And because of this, you can see that for any point inside here, all of the field lines are going to essentially cancel out. So the whole interior, there's going to be no electric field within the conductor. And also just, remember, like in the last presentation, that you can charge conductors via induction. So this is where we took a conductor, we took a charged rod, we put it next to the conductor, and because the charges are free to roam around, we saw that the charges were displaced within the conductor, and then we would ground the conductor, so we would let go of some charges, and then we move out the rod that was charged, and then we're left with the conductor being charged. So this is induction. A conductor can be completely polarized in the presence of an electric field. You put a conductor in an electric field, and you'll see the particles, they'll move in accordance to the electric field. Electrostatic shielding is the process of surrounding an area by a completely closed conductor to create a region free of an electric field. So if you're sitting inside of a spherical conductor, like imagine a big sphere around you, there's an electric field inside, right? So you're being shielded. Some more properties. So yeah, we just went over induction. This is from last week. I won't repeat it. A charged object can attract a neutral conductor. So essentially, this is kind of similar to what we were looking at with induction. So the conductor can be polarized, right? So if you have a charged object, which is literally the metallic rod, and then using some tricks where you can use induction to you can attract a neutral conductor, because you essentially don't ground it, and then you maintain a neutral conductor, and by moving around the particles and using this charged object, you can attract it. Now, the net charge on a system is constant. So if you have two connected spheres connected by a wire, the charges will redistribute so they are at the same potential. Okay, so we've talked about conductors. Now we're going to look at capacitors. So what is a capacitor? So it's literally the combination of a positive charge and a negative charge, and that's a simple capacitor. And usually, if you look at chips, if you look at other electronic devices, you often see a parallel plate capacitor. So instead of being charged, it'll be a plate that's filled with charges. So you have one plate that's positive charges and one plate that's negative charges. If the conductors carry charges of equal magnitude and opposite sign, a potential difference exists between them. So what this is saying is that you have plate A over here with charge plus Q. Q is measured in coulombs. You have another plate of equal and opposite sign charge. So this is minus Q. Then there's a potential difference. And the special thing is that the potential difference and the amount of charge has a special relationship. So what this is saying is that the relationship is linear. And the constant proportionality for this linear relationship is C, which we define to be the capacitance. So I'll say that again. And a simple way to think about this is you can see by observation, if you pull out some capacitors and a voltmeter and do some measurements, you'll see that if you double the amount of charge on the plates, so instead of being Q, if this becomes 2Q and this becomes minus 2Q, you'll see that the voltage also doubles. So you see this linear relationship. And you can plot Q and you can plot V, and you can see here it's saying that delta V is equal to Q divided by C. And another way of writing this is Q is equal to C delta V. You can see that I guess I won't plot it because there's multiple ways to plot it. But you can see that if you double your V, then Q also doubles. So in this case here, you have a graph that looks like this over here, where if you double V, your Q also increases, where the slope of this line here, M, is equal to C. So experimentally, we've determined that it's a linear relationship, and we assign capacitance to be the constant of proportionality. So when we talk about capacitors, we can just define it by their capacitance. And then you kind of just know that if you apply a charge to it, then you can say like how much voltage you'll get across the plates. Now this is always a positive quantity and it's measured in farads, F. Okay, so think of capacitance as capacity. So it helps us understand how much charge two plates can hold if they're at a certain potential apart. It can also help us understand how much potential there'll be if we charge the plates to a certain amount. And it turns out that 1 farad is extremely big. So 1 farad is just a coulomb per volt. It's really big, and in real life we often deal with like nano or picofarads capacitors, sometimes millifarad capacitors. So you'll rarely, this is huge. We should get a picture for next year for what it looks like. So a parallel plate capacitor, and this is this picture over here, parallel plates, plus Q minus Q. The surface area of a single plate is A, and they're separated by a distance D. So a parallel plate capacitor separated by a distance D with plate surface area A. Well, the capacitance, which is a constant proportionality, which is defined to be Q divided by V, turns out to be equal to epsilon 0 A divided by D. So epsilon 0 is the same epsilon 0 we've seen earlier, the permeability of free space, and A is the area, surface area, and D is the separation. So if we want to have a really high capacitance capacitor, it has high capacity to hold charge, then we could bump up A, we could make them really big plates, or we could bring them really close to each other, and that would also increase the capacitance. And you can think like on your smartphone, for example, like does it make more sense to double the area of the capacitors, or does it make more sense to bring the distance between the plates closer? And also physically, like where is the limiting factor? You can only bring the plates so close before some of these approximations don't hold. Another thing that we have is the energy in a capacitor. So we will see this probably later on, but the energy of a capacitor is given by one of these three formulas, Q squared over 2C. If you substitute in C is equal to Q over V, then you end up getting this formula here. And similarly, if you substitute over here if you substitute in the second formula here for Q, then you end up getting this third formula, 1/2 C times the voltage squared. And the conservation of charge and energy can be applied to a closed physical system containing charged capacitors and a source of potential difference. Alright, so some properties of capacitors. So the electric fields of oppositely charged plates can be actually determined by Gauss's law. We can draw a surface, a Gaussian surface, and using that we can derive the electric field strength. Now the electric field between two plates of a parallel plate capacitor has these following properties. The electric field is constant in magnitude and is independent of the geometry of the capacitors. So they just have to be parallel plates. It doesn't really matter the shape of these plates. They don't have to be squares. They can be whatever they want. And it's independent of the shape. Now, the electric field is proportional to the surface charge density of the charge on one plate. So all this is saying is that if you want to determine the electric field, it's proportional to the surface charge density. So this is saying that I guess one thing just to remember, just to recall real quick, is that we said that for conductors, you place a charge on a conductor, it'll evenly disperse. That's why we can say that, for a given plate, there's such thing as a surface charge density, the charge per square centimeter, square meter. And once we've determined that, the electric field, of course, is going to be proportional to that because it's proportional to charge. Now, the type of questions we're going to see, especially in the next lesson, which is going to be circuits, is how to combine different capacitors. And there's two main configurations. So you have series, where both capacitors, they occur right after each other. So this is an example of two capacitors in series. So this is one parallel plate capacitor, there's another one here, and there's like a wire connecting the two. So like if there's a which we'll look at soon, is that basically if we were to have a current, which we'll define soon, going through, it'll go through the first capacitor and then the second capacitor occur in series. But for our purposes here, what we're looking to do is, given this series configuration, how can we replace this with one equivalent capacitor that has the same capacitance as both of these in series? And the other type, the other flavor, is parallel. So there's a split and the plates are literally parallel to each other. I guess the diagram cut off a little bit, but it would look kind of like this here. You would have a wire and charges are free to split between the two capacitors and they regroup back over here. And I guess a good way to do this is to, follow the wire. Like you see here that there's a path where it only goes through one, and there's a path where it only goes through the other. They're both in parallel. Versus here, there's only one path, and the only path, it intersects both capacitors. So that's kind of how you can quickly tell if it's in series or if it's in parallel. And so when in doubt, I guess a more scientific way of doing this is to examine the electric field lines if they occur serially or if the fields are in parallel, the capacitors are in parallel. And just to be clear one more time, what our goal is to do is that we want to replace these two configurations with some equivalent capacitor, CEQ, such that CEQ, C equivalent, has the same capacitance as this configuration here. So if you hide this in like a black box, if you hide this here in a black box, and you have another black box, which is this equivalent capacitor, you would have no way of knowing which one's which because they'll both behave the same. And that's the key here. We're looking for one capacitor that behaves the same as two capacitors in series, or one capacitor that behaves the same as two capacitors in parallel. Now, the way that we can solve this is that in series, it turns out that the equivalent capacitance is just the sum of the capacitance of the two plates. And for parallel, we're having some technical difficulties. Be right back. Okay, and we're back. There's a big mistake on the slides which I've now corrected. Audio check. Okay, we're good. Okay, so yeah, my mistake on this. Okay, slides now fixed. So basically, we just left off saying that our goal here is to combine a series configuration to give us an equivalent capacitance, and the same thing for parallel. And the way that we can do this is that for two capacitors that are in series over here, the way that we combine the two is by this formula here. The equivalent capacitance is equal to the reciprocal summed and the negative one, the harmonic mean. And the equivalent for two capacitors in parallel is that we just sum up the two capacitances. So the way that I remember this, which is kind of, I don't know if this is a good idea, is that for parallel I just imagine a big capacitor and it just adds like that. For series I think that, oh well, it's going to be slightly less. Just a mnemonic. Now dielectrics are a super important concept, and we just talked about capacitors, and in these capacitors here there is an air gap basically between the plates, and for dielectrics we're going to actually insert a material in between. So a dielectric is a non-conducting material, so it's rubber, glass, or wax paper, and it's inserted between the plates of the capacitor. And using a voltmeter, if we measure the voltage between the plates before and after inserting the dielectric, we'll see that the dielectric actually increases the voltage by a positive factor greater than 1. And we call this increase in voltage the dielectric constant. And the dielectric we say that a dielectric changes the capacitance of the material by a factor of kappa, by a factor of that dielectric constant. So essentially, if C0 is the initial capacitance, and all we do is we keep the charges the same on the plate, we just insert a material with dielectric constant K, or kappa, then the resulting capacitance is now kappa times that initial capacitance. So it increases the capacitance, it increases the capacity. So now because C equals Q over V, if capacitance goes up and if Q is the same, then you can see that the voltage will also go up. Now, over here, we see that the dielectric changes the capacitance of the material by a factor of kappa greater than 1. So for a parallel plate capacitor with a dielectric, the capacitance is given by kappa times epsilon 0 A over D. So if we go all the way back up, conductors, capacitors, we have C is equal to epsilon 0 A over D. And essentially, because the capacitance is multiplied by a constant after inserting the material, then this is also multiplied by that same constant. So it carries through. All right. Where were we? Right here. I think I misspoke here. I think yeah, the voltage will actually go down, right? Yeah, the voltage will go down if we have the same amount of charge. I guess a cool thing. So adding a dielectric increases the capacitance, and the interesting thing is that when you add in a material like an insulator, because the charges are bound to the atom, they're still able to kind of rotate. Like you still have the charge bound to the atom, but where they are in the atom, they can still like lean to one side or the other. And what happens is that because there's a material in here, and because there's an electric field due to the capacitor, there's always the electric field, you can become partially polarized, and actually the dielectric itself will create an additional field. And it turns out that this additional field goes in the opposite direction, so the overall voltage between the two drops. So a better way of thinking about this is that, a more visual way rather, is that you have your parallel plate capacitor here, and you have positive charges here, you have negative charges on your plate, and this creates, the electric field, right? Creates this electric field. And when you put the material, the dielectric material, in between, what's going to happen is that this material itself, the positive, the positive part, like each atom, the positive part is going to be slightly leaning towards the right side to this metal plate on the surface. So if you look at if you look at the surface of the insulator, it's going to be leaning kind of positive on the surface and negative right below. And this is per charge, because the charges are bound to the atoms. So what happens is that the surface here contains all the positive, slightly positive charge, right? And right underneath that are negative charges, and because of that negative, you have positive charges for the atoms right next to it, and then you got negative, and then positive, negative. And on the opposite side, the exact opposite happens. On the surface, you have negative charges leaning towards the parallel plate that's positively charged. So you get this kind of configuration, and because of this here, you end up getting a field. And it's going to basically reduce the strength of the field, which then affects the voltage. So here's some advantages to dielectric. So it increases capacitance, right? We saw that C equals kappa times C0, and it increases the maximum operating voltage. It increases the available space on a chip. So now, we can insert a material in between the two, which increases our capacitance. So earlier we were saying that since C is proportional to A over D, we were saying that the only way to increase capacitance is to make a bigger plate or to decrease the separation. But what we can do instead is we can put in a dielectric material, and that will also increase our capacitance. That's another option. Yeah, so we can actually scale down two ways. We can the best way to scale down is we can decrease A, and we can so this would be C0, and then C is equal to kappa times C0. So what we would do is we would insert a material, so we get the factor of K over here, and then we would decrease A, and then we would decrease D. So we bring the chip closer together, the plates closer together, insert a material, and that allows us to have smaller plate sizes, so we have more room on the chip. And this is a cool table here with the different properties of materials. So here it tells you about the dielectric constant of the materials. And you can see that air, which is what we normally use, is approximately equal to 1. And a vacuum over here is almost equal to 1. Now, let's look at an example. So one example for today. And what we're basically looking at here is that we have a square plate capacitor. Keyword is square plate. So when we think about our area of the plate, just remember it's a square. And we have this dielectric material in this region, kappa 1. The dielectric constant is kappa 1. And on this half, we have two dielectrics. So one is kappa 2, the other one is kappa 3. and this is distance d over 3 and distance 2d over 3. The full distance is d, and this is L over 2, and this is another L over 2. And the way that we can do this is we can just, we can just combine the series and parallel combinations. So earlier we were looking at explicit capacitors, but now what we can do instead is we can notice that we can do the same thing with these. We can do the same thing with these dielectric constants. So what we're going to say is that I guess we'll start by defining that the C1, C2, C3 are just the raw capacitance without the dielectric material. So the combination of 2 and 3, which is these two, and I guess just to take a step back, how do we actually solve this? Well, we kind of have a series combination here, and we have a parallel here and a parallel here. But the best way to solve this is to actually combine these two series into one dielectric material, or one capacitor, and then combine the two parallel. Does that make sense? So we first reduce this into one thing, and then we reduce both of these into one thing, and then we essentially have just one capacitor that we can solve for. So if we combine this K2 and K3, I'll start saying K instead of kappa. The equivalent capacitance is given by, remember, it's the 1 over C1 plus 1 over C2. So we got 1 over, this time instead of just being C2, it's kappa 2 times C2, because K2 times C2, because there's a dielectric material. So K2 times C2, and then K3 times C3, and if you do the math over here, you end up getting this expression. And now this becomes our equivalent. So now it kind of looks like this here. We have K1, and now we have this, we have basically C2, 3 over here. So this part of the capacitor here is C1, and this part here is C2, 3. So now what we have to do is we have to combine this parallel combination. We have to combine these two capacitors that are kind of in parallel. And the way that we do that is pretty easy, right? We just sum both of them up, sum up the capacitances. So the capacitance of this left part is just kappa 1 times C1. And the capacitance of this right part is, well, we just calculated that. It's this C23 expression over here. So we end up getting this over here as the equivalent capacitance. But there's a problem, right? We only want to express it in terms of C0, K1, K2, K3. So we have C1, C2, and C3 in the expression, so we need to get each one of those in terms of C0. And remember, C1 is this capacitor, C2 is this capacitor here, and then C3 is this capacitor here. And C1, and you can scroll up again, but remember C equals kappa times epsilon 0 times A divided by D. And because we're not dealing with dielectrics, right, we said that C1 is just the capacitor without the dielectric. We just end up getting epsilon 0 times A, which is a square plate capacitor, so it's L divided by 2 quantity squared, which becomes L squared over 4, divided by D, which is this, and then C2 is just epsilon times A squared, which again is L over 2 squared, divided by the distance over here, which is D over 3. And then the third one is the same thing, but the distance is 2D over 3. So you end up getting this, this, and this. And just remember, C0 is epsilon 0 times L squared over D. It's just the C0 is this capacitor here. So if we substitute all of these into our expression over here, we end up getting this mess here, which is then equal to this over here. So you can see by if we want a certain capacitance and we have three materials, there's a big range of possible basically effective kappas that we could get. And that's it for today, and next time we'll be covering circuits. Thank you for coming.